Okay, if you remember, I left you with the design after the boundary and excitation setup. Now what you want to do is you want to see if everything is fine. It is fine, and then you do the analysis. And as you can see, it's pretty damn fast, which is good for us because you want to do a parameter search and whatever you want to do. It's good to have a fast simulations. Now I'm working with different type of softwares, and each time I'm doing a mistake, how you can pan around. Okay, so let's check out what we have. To do that, you just right click on the analysis and you go on what the heck. Okay, you right click on the analysis or setup that you have and you go to the profile, coverage, solutions, whatever you want. Let's go with the solution data for this time and see what we have. What we have here is force at the parameter force that is calculated, and it gives you the force in Newton, and you can make it to be micronewton, and you get like pretty small amount of force, and you get no force on y-axis, which is true because the cross basically the cross product of the magnetic field and the magnetic field that you have is basically like this or like this, and the cross of that is going to be on the x, and it's going to be the negative. Okay, so that's good. So the force is true. I mean, it's like at least in the right directions. And what you can see is I'm going to also show you how to change the force. This is the DC force. Okay, now you can have the AC force as well, and let's go with the magnitude and the real, and you can see how much AC force we have. And again, in the Y we have a very little AC, but in the X we have quite a bit of AC force. And you can also change it to the magnitude and phase for the force, and you can see that we have a magnitude of 5 micronewton for the force, and the rest is basically simple. Or you can make it radian or degree. Okay, these are cool. Let me show you one last thing, and that is, here it's adaptive pass. So when you do the adaptive pass, and you can see in different passes how the force actually evolved. So you can see that the very first pass, the force that was calculated was pretty off. It was let's go with the magnitude of the force was 3.88, and then in the second pass it becomes 5.43, and then it becomes 4.78, which is pretty off. And what I'm doing is just pressing the down key to basically go through the different passes. Right now we're in the pass 4 as highlighted, and the force was 4.85, still not good. The pass 5, the force becomes very close to what we have right now, which is 5.0076. And then if you look at the y force, it's still big. And when you go one more pass, you can see that the x force changed not that much, but the y force is still getting like quite a bit of a change relatively to the size. And when you go to the pass 8, you can see basically things are getting pretty much accurate. And when you go to the higher number of pass, you can see the changes are pretty insignificant. Okay, so this is a good news. When you are doing the EM simulations based on the engine that they have, most of the time it's a good thing to check how it reacts between the different passes. You want to see something like that. Okay, and okay, great. Now what I'm going to do here is I'm going to go and plot for you the forces that we have. But as I said, we want to know the Lorentz force, and we want to be able to plot that versus the phase. And in these conditions, because we don't have these kind of equations, I'm going to use the calculator to basically start making first the the force, the DC Lorentz force, and then we are going to have the AC Lorentz force, and then we will add the AC and DC Lorentz force, and basically we make the instantaneous force, and we'll plot that later. So let's open up the calculator by just right clicking on the fields, and right there it's a calculator, and let's go with the quantity and select J for the quantity, and we want to have a cross product of the J and B, so we go on the quantity B now. As I said before, this is a stack calculator, and these calculators are a bit different than the one that you are used to work with. So basically how it works is it remembers the last items, and when you select item A and then you select item B and then you say times, it will times A times 2B, and then gives you the results. Okay, this is the very weird calculator, but you will get used to it very soon. It's very common in the engineering softwares, this type of calculators. So as I said, you select the J and then you select the B, and then you will select you will say that I want to make sure that the B is complex conjugate. So I would go on the complex side of that and make it complex conjugate. So complex conjugate. Okay, now that it's complex conjugate, let's go and do the cross. So we have the cross of J with complex conjugate of B. Awesome, right? Then make sure that everything is going to be scalar. Sorry, here, the scalar x. So I'm gonna look at the force at x. We know that it's only in x directions, so we look at the x, and we go and say what's the real part of that. So we go to the complex and we say what is the real of that. Okay, and then we have to do integral. So what we should do is we should go to the geometry and say the volume, and in the volume we go and say the left, because we are doing over the volume that we have J inside, which is the left. Other than that, all the volumes does not have J on it, so 0. So press OK on that, and we say the integral of that. Okay, and that's it. Now we can say add, and then we call it force. Here is the DC force. Okay, press OK on that. Same thing we want to do, so I'm doing it fast. J times B, it's going to be a cross, and it's going to be the scalar x, and it's going to be the what I'm going to do now, it's going to be the function, and then it's going to be the phase, and it's going to be a complex at phase, so that's going to be at phase. And then it's going to be number, and it's going to be a scalar number of 0.5, which is half of that, and then pressing OK for that. Oops, so I forgot to put the 0.5 on the top one, I I'm gonna fix it later, but I'm not gonna show it in this video. Okay, so just do the same thing that I've done for the AC. Just you say click number and then 0.5 and then press OK and then say multiply that by that and then go to the geometry and then select the volume left and then you go and say integral and then we call it force AC. Okay, so do the same thing for the DC. Just make sure that you're putting the 0.5 for that as well. Okay, I did correct the forces. Now what we are going to do again is to want to have the calculator open again, and we want to have the instantaneous force. Instantaneous force, as I said, is the sum of the AC and the DC. So we can select AC and we can select the DC, and then we can say copy them. Oh, let's do it one by one. Copy that, and then you select the DC and then you say copy that, and then you say sum them up, add, and now we can save that, and we can call it force instantaneous. Okay, so that is the final product that we wanted to do, and that's it. We are done with that. So let's go to the result and create field report, and then in that you go to the rectangular plot, and then over there you go and select the phase for the primary sweep, and then also you go to the calculator expressions, and you basically want to select the three AC, DC, and instantaneous by just pressing and holding the control key and selecting on them, and you can go and select a new report. Okay. So what you can do here is you can right click on that and you can say sorry, trace characteristics. Okay, and then you can say add, and then in the category of the math we want to have the maximum of the function maximum, so it will basically shows the maximum of that, and press add. So now we have that, and then you can select, and now what I'm going to do is I'm going to go to the general and make sure that it's a scientific representation of the numbers. So there we go. Now we have numbers here for the maximum of the peak for each of these, and you know, the 5 micro newtons is actually shown here. Okay, so this is a force that we have, and one funny thing that you can see here is that the force is fluctuating here twice the frequency of the excitations, and that means that from 0 to 365, sorry, 0 to 360 degrees, we have 2 cycles of force, and the reason for that is basically because we have 2 magnetic fields and also the J current fluctuating, and that will basically make 4 different cases in each cycle of those. So we have a magnetic field that is cycling in 100 kilohertz, and then we have a J that is cycling in 103 kilohertz, and they are not in the same what do you call it, okay, yeah, this is a DC one, and as you can see, the DC and then the AC, which is on top of each other. What I'll say, yeah, so because of that, we have twice the frequency, because one is cycling, the other one is also cycling with a different phase, so it will create a twice effect. Okay. One last thing is that the instantaneous force that we have on the left bus bar is can be calculated with another method, and that method is the stress tensor method. This is different. This is a bit different than the Lorentz force and the virtual force that we saw here. So we saw the Lorentz force right there in the very beginning. It was calculated automatically, and we saw the solution data. And then we did calculate the the virtual force. We saw that in the beginning, and then we saw how to calculate the Lorentz force right there. You can see the sine waves here, and now. This is the third method, which is the stress tensor, and this is extremely sensitive to the mesh, and it really related to the way that we defined our accuracy. And so because we have a very good accuracy in this design, we should have a very accurate mesh, and we should be able to see sort of the same calculations for that. So now if you want to calculate the stress tensor, the force, instantaneous force using the stress tensor, this is the equations for that. As you can see, you have the dot product of the B and N, and then we times it by H, which sort of represents the J. Okay, and let's go ahead and try to evaluate that for each phase. Okay, this is a phase dependent, by the way, as this one was the first dependent, the Lorentz force. The tensor one is also the phase dependent, so you have to have in your calculation in phase, or at phase, sorry, in at phase. So basically you can see that in different phases you have different values. Okay, so let's go and open up the calculator one more time, and this time I'm going to go and select the quantity of B, the magnetic field density, and then in the functions I'm going to have basically the phase of B. You know, I'm interested to the phase of B, and also I want to make sure that I'm doing at phase, so everything is going to be calculated at phase. And what else? Well, let's go to the geometry and select a line, and make sure that we are selecting the boundary line of the left bus bar. Okay, and then you will go to the unit vector, okay, and you select normal of that boundary that you just selected, and then we say we want to have a dot product, and then we go to this quantity H, the quantity H, and then same thing, we go to the function, we say phase, and then we go to the complex and we say at phase, and then we go to the then now we have to multiply these two guys together, right? Because this is the at phase H, and then we have a dot product of the B at the norm of the line. So we multiply these together. So we have the very first section of the equations, which was B dot normal times H, and then we have to minus half of the B dot H at the normal, and then we go over an integral of the dV. Okay, as you can see in this formula. Okay, so we covered the first half of that. So let's go and create the other half. So we will have B, and then we would have function phase. Of course it's going to be at phase, and it's going to also we select H. Let's do that, select H. And then also we want to go and say we want to have the function of phase, and as you guessed, at phase, and then we want to have a dot product of that, right? If you look at the formula, and we will have a dot product of that, and now we want to have the number. I know that this is getting pretty damn annoying, but you know, it's a big formula, you have to basically deal with it. So I'm having times 0.5, and then we will time it by that, and finally we go to the geometry and we select a line, and we are trying to find the normal of the line for the left. So we basically say left, and then on the unit vector we go and select normal. Now you want to multiply that. There we go. So we're almost there. Now we need to subtract these two from each other, so I'm pressing negative, and then I'm gonna say so this is negative, basically says this is negative, and then I'm gonna put plus. So this is a bit stupid, so let's undo the negative sign and then go for the negative negative here, and then you say plus, so it adds the negative of that, which is minus, but let's do it like that, okay? And then go to the scale, and then a scalar x, we are just interested to x. Go to the geometry, and then go to the line, and then go to the left, and voila. Lastly, integrate. And did I say integrate? Yes. And at the end, so it's just so long that it doesn't show it right. So this is good. I thought it's 2 lines. And press add, and you know, we can call it the force that is based on tensors and stress tensors. So stress tensors, and press OK on that, and done. Okay, so you know, the interesting thing would be to plot that, and I'm gonna do that again. So create field report, and then I'll select the MST, and then make sure that we are doing it on over the phase, and new plot, and we got the thing. And you know, I think you need to do the scientific. That's actually pretty it's pretty good, but it's not actually let me delete this, and oh no, sorry, let me just add the instantaneous as well on top of this, and that would be at trace. So you can see the difference here. It's not that much, but you know, you have some differences. But you know, there are 2 methods to calculate that, and the tensors one is a bit sensitive, but you know, you get pretty good results. I mean, honestly, it's pretty nice. And so that annoying calculations that we've done was the advanced part of the eddy current solutions, and you guys know a lot now, and go ahead and exercise more with the calculator. You can do way more stuff with the stuff that I told you here, and you know, you can use it for your designs. Next stop is going to be the 3D model of that, and see how much differences we get, and why we should go to the 3D model sometimes. These are all answers that will questions that will be answered in the next tutorials. Before I finish this tutorial, I'm going to tell you that I'm doing a lot of things here for, you know, free of charge, and I would love you guys to, if you have any questions, put it underneath each videos, because it's very hard for me to go through all the videos that I have in this channel. So make sure that your questions are not in the discussion. It's not as a message in the YouTube channel, because I hate those environment of the channel that is like so hard to go through the channel, the message senders. So just put it as a comment. And if you do have some designs and you don't want to do it yourself and you don't have time, I am okay to do those things with the premium like support, and I do charge. So if you think that you cannot pay or you're not able to pay, I'm super busy with all these designs that coming towards, and I would love to help you as much as I can for free, but honestly it's not very possible. So anyway, if you have a design and you want to do me doing it for you, you can send it to my email, and as you can see, the email is right there, and I will take a look at it and give you my feedback on that. Okay, these are all the stuff that I was going to tell you. If you like to share these videos, please share it with the YouTube channel. I mean, within the YouTube channel you have all the shared links, and you can do that as well. Okay, great. Have a great day and enjoy.